let's check out the area of a parallelogram, a four-sided shape with opposite parallel sides. Instead of just memorizing a formula, let's see how the formula works and gain some insight that can help us work with other, more complex shapes. We'll start with a box of playing cards. We can calculate the volume of the box by measuring its width, height, and length, and multiplying those values together. If we remove the deck of cards, we can see the stack has essentially the same volume as the box. We can cut the deck in half and put the two halves together. We've made a shape with a different width, height, and depth, but the overall volume is unchanged. No matter how we split up and rearrange the deck, as long as we don't add or remove any cards, the volume is constant. The same is true for area. The surface area of a card is the length times the width. We can cut up the card and rearrange it into a different shape, but the area remains unchanged. This gives us a useful tool for figuring out the volume or area of complex shapes. We can cut them up and rearrange them into forms that are easier to measure. Beyond rearranging the deck of cards, we could also skew it to the side. Shifting the deck like this also doesn't change its overall volume. The length of the edges on the sides does grow as the cards slide over each other, but the thickness of the deck remains the same. This kind of transformation is called shearing. Shearing a solid object will transform it without changing the volume. To get a clearer picture of what shearing is, we could also take our empty card box and pitch it to the side like this. What we're doing to the box isn't shearing, since the box can collapse flat, losing all volume. For the deck of cards to shear, one edge has to stretch, as the thickness stays the same. In the box, the sides are all rigid, and the thickness collapses. It's also possible to shear flat shapes and not change the surface area. In the case of our parallelogram, we could shear it to have right angles, making a rectangle, which has an area of base times height. Or we could use our method of cutting and rearranging to slice off the slanted edge and move it to the other side, again making a rectangle. With either method, we can see the area of the parallelogram is its base times height. The process of cutting and rearranging and shearing go beyond just parallelograms. They can be used to transform all types of complex geometry into easier to measure forms.